So if you think about it, you have, oops, there we are, positive charge here, and a negative charge here. There's a force in that direction from that one, force in that direction from that one. The net force looks like that, upward, right? And that would be the correct answer. Had almost everybody. Don't worry, we just sort of take attendance with the thing. So the correct answer here is up, C. All right. What about the electric field due to a negative charge? How does it look? Well, you just turn the arrows around. The field points inward toward a negative charge. So we draw it exactly the same way as we did for a positive charge, except all the field lines point in. Why is that? Well, if you brought a positive charge over here, it would feel attracted to the negative charge. And so, we have an electric field then which points in the direction of the force on the positive test charge, and that force is in toward the negative charge. So what if we put a positive and a negative charge together? Well, once again, we have the field lines radiating outward from the positive charge and radiating inward toward the negative charge. If we just add them vectorially, we get something that looks like this. And this is sort of the class, yes, sir?
Why is it in chemistry that we refer to the opposite, as in the negative moves towards positive? And then in this...
Well, electric fields go from positive to negative. Whatever they're teaching you in chemistry, clearly we have a self-consistent mathematical description, right? Which you have a positive force radially outward on a positive charge. In chemistry, they wouldn't say that two positives are attracted to each other. So you wouldn't say the electric field is the other way, would you, in chemistry?
No, it's just that the negative charge usually moves towards a positive.
Well, a negative charge here does move toward a positive charge. Isn't that what we said?
Yeah. Use the
So the electric field originates on positive charges and it ends on negative charges. I think that's the same in chemistry too. Maybe you should dig out what it is you're.
I think he's talking about like transfer of electrons, stuff like that. Electrons will transfer from that to the other side.
Well, an electron is negatively charged, so it will. So suppose we put an electron here. So here we have a positive charge and a negative charge creating this dipole field. Now we bring in an electron. Which way is it going to go? It will go to the positive. An electron moves against the electric field, right? Because it's negatively charged. Right. Electrons do go from negative to positive, for sure. Yeah. Maybe that's the source of, yeah. I mean when we define electronegativity for an atom or something like that. Same idea. But it's ultimately due to the physics, the electric field. So yes, if you have positive and negative, it looks like this. The electric field in between, directly in between the two, is just a straight line. And then it goes over to the other side. These lines, if you kept drawing them out here, would curl around. This is the same line as this one. And if you could draw it in 3 dimensions, you would see lines coming out of the screen and going back into the screen, hitting the negative charge. So when we give you an arrangement of charges and ask you to draw the electric field lines between them, that should be the rule. That you have a certain number of lines coming out of this charge corresponding to how big the charge is. If this one is twice as big as this one, it would have twice as many field lines coming out. And they go out of a positive charge and terminate on a negative charge somewhere in space. Yes?
I'm trying to understand the source of confusion for this gentleman because you see a force going toward this electric.
Well, what you see is the electric field, right?
Charge, but then the force is pushing it, but then it's still being attracted the positive charge.
Well, a negative charge would go opposite the electric field, right? Because it's negative.
It's just the direction of the electric charge, but that charge is in fact, or I'm sorry, the
electric field itself.
The electric field is attracting it, even though it's reaching it in that way. The
Yeah.
electric field, yeah, is reaching it.
I think
that
it's a
way,
whole.
but
I think it's self-consistent. If you take into account the negative charge on an electron, that's why I say, it might have been better if Ben Franklin had chosen the other convention. It would be easier to teach. Anyway.
Cool. So yeah, that's just the electric field reaching the negatively charged particle, but it's in fact pulling it.
Yeah. Electrons move opposite the direction of the electric field. Yes.
So if one charge is bigger than has more lines,
Yes.
then where would they go? Because they wouldn't end up on the
They have to find some other charge. Ultimately, we think, we have no reason to believe the universe as a whole has a net electric charge. We think there's equal numbers of positive and negative charges, as far as we can tell. So eventually, the field line finds a negative charge on which to terminate. Yeah. But that's a good question. Now, when you draw that, how do you draw it? Well, if this one on the left were twice as big, you might have, rather than 6 lines coming out, you might have 12 lines, 6 of which terminate on this one if it's half as much charge, for example. That would be a good way to represent that. Yeah. And we're going to show distributions, much more complicated distributions of charges, starting with this one. So this is just some sort of random assemblage of positive charges in blue and negative charges in red. And it's pretty easy to write a computer program to show the electric field lines here. And we draw them as field lines. It's really not, it's kind of a good way to represent electric fields. It certainly shows you the direction of the electric field. And you can see the little arrowheads pointing from the positive charges to the negative charges. And here the strongest charges are these two, and you can see this dipole field-like pattern in between them. But because there are other positive charges and those field lines sort of repel each other, you get this region here where the field goes to nearly 0, etc. But all you would have to do to write a computer program to do this is, for any point in space, you just calculate the electric field due to each of the charges and add them up vectorially and then draw a line, okay, pointing in that direction. And you could, for example, follow those lines like so. Now, as you can see, it can get quite complicated. Imagine if this represented, and for all I know it does represent, some section of some molecule somewhere. And as you know, different atoms in molecules can either have slightly excess or a slight deficit of electrons near them, giving them a net positive or a net negative charge. For example, why do any two atoms stick together? Well, because you have these unfilled orbitals, right? And that each atom tends to polarize the other, creating a dipole moment in the other one, and then they stick together. That's how chemical bonds work. And that's why the interatomic forces in molecules are due to separation of positive and negative charges.